Tonight, we're going to explore one of the strangest ideas in all of science, the light year. Our nearest star beyond the sun is so far away that, even with the fastest spacecraft we've ever built, it would take about 6,800 years to get there. You've probably heard phrases like 10 light years away or a galaxy 10 billion light years from Earth, more times than you can count. But almost nobody really understands what those words actually mean. The phrase is everywhere. It's so common that our brains start to treat it like background noise, just another big impressive sounding word from astronomy. But if you stop for a moment and actually ask, what does that really mean? Things start to get very strange very quickly, because a light year isn't just a long distance. It isn't just a big number you nod at and forget. When you really understand what a light year represents, how much space it actually covers, it changes the way you see everything in the night sky. It changes how you think about travel, about time, about our chances of visiting other stars. It even changes how you see your own life here on this small world. Most people carry around a vague idea that a light year has something to do with time, maybe a year of traveling at light speed. They know it's huge, but that's about it. And that's understandable because our everyday experience has not prepared us for distances on this scale. Our brains did not evolve to deal with trillions of anything, let alone trillions of kilometers of empty space. So tonight, we're going to slow everything down. We're going to peel this concept apart gently, one layer at a time, until it stops being just a dramatic word and becomes something you can actually feel. Not perfectly, no human brain can truly feel distances this large, but enough that when you hear 10 light years away or 100,000 light years across, you'll have an intuitive sense of what that really means. By the end of this journey together, you'll understand three things very clearly. First, what a light year actually is. Not just the textbook definition, but how it connects to the speed of light, to the way information moves through the universe, and to the way we literally see the past every time we look at the stars. Second, why ordinary units like kilometers and miles completely fall apart when we try to use them in space. We'll see exactly where they stop being helpful, and why astronomers had no choice but to invent something new. And third, what light years silently tell us about our place in the cosmos, about how far away our nearest stellar neighbors really are, about what it would take to ever visit them, and about why the universe might be full of life and still feel completely silent. This isn't going to be a quick list of facts. Think of it instead as a long, calm walk away from Earth. We'll start from distances you know well, across a room, across a city, around the world, and step by step we'll move outward, to the moon, to the sun, to the other planets, to nearby stars, to the Milky Way, and finally to the edge of the observable universe. At each step, we'll ask, how many light seconds? How many light minutes? How many light years? And what does that actually mean for us? If you enjoy these kinds of deep, slow explorations of big ideas, a quick like or subscribe really helps the channel more than you might think. It's a small gesture on your side, but it makes it much easier for me to keep making long, detailed journeys like this one. For now, though, you don't need to do anything except get comfortable, maybe dim the lights and let your mind stretch a little. Because to understand a light year, we first have to talk about distances we can understand, the ones here on Earth, at the scale of our everyday lives. Let's start close to home. When you think about distance in your everyday life, you almost never think in trillions of anything. You think in short, simple stretches that your body and your memory understand. You know how far it is from your bedroom to the kitchen, from your front door to the corner store, from your house to your workplace, your school, your favorite cafe. Maybe it's a 10-minute walk, or a 15-minute bus ride, or a 20-minute drive. You don't usually think, that's 3.4 kilometers. You think, that's about 20 minutes. The same is true across a town or city. You know which places are close, which are a bit of a drive, and which are on the other side of the city. Maybe crossing town takes you half an hour, maybe an hour if there's traffic. You've done it enough times that your brain has built a map that connects distance to time and effort. You can picture the roads, the buildings you pass, the lights that always seem to turn red. Even when we do think in numbers, they're still tied to our bodies. At a normal pace, you can walk about 1 kilometer in 10 to 12 minutes. If someone tells you a park is 1 kilometer away, you don't just hear 1,000 meters. You feel it. That's about a 10-minute walk. If they say it's 5 kilometers away, you think that's maybe an hour on foot or a short drive. Driving stretches this a little further. Across a city, a few kilometers might be 10 or 15 minutes. Between cities, a couple of 100 kilometers might be a 2 or 3 hour trip. If I tell you a town is 200 kilometers away along a highway, you probably imagine something like fill up the tank, maybe grab a coffee, set some music, and settle in for a couple of hours behind the wheel. You might even know that at 100 kilometers per hour, 200 kilometers is roughly a 2-hour drive. The number plugs directly into your experience. Let's scale up a bit more. The distance all the way around Earth at the equator is about 40,000 kilometers. That sounds big, but even that is still something our minds can almost handle because humans have actually done it. Early explorers sailed around the world in wooden ships, taking months or years. Today, commercial airliners can circle the planet in less than 2 days if you could string together the right flights. There are even record attempts where specialized aircraft have done it in under 48 hours. You and I may never personally fly all the way around the world in one continuous trip, but we know it's possible. We can imagine it. A long sequence of flights, airports, time zones, sunrises, and sunsets. We understand that if you keep going east or west long enough, you'll eventually come back to where you started. So even 40,000 kilometers doesn't feel completely alien. It's extreme, but it still sits inside the realm of human achievement. These are the kinds of distances our brains are built to understand. They all have 3 things in common. 1. You can either travel them or imagine traveling them. You've walked 1 kilometer. You've driven tens or hundreds of kilometers. You've flown hundreds or thousands. 2. You can convert them into time without thinking very hard. 1 kilometer, 10-minute walk. 10 kilometers, short drive. 200 kilometers, a couple of hours on the road. 40,000 kilometers, a long, exhausting series of flights. 3. You can attach experiences and sensations to them. Sore legs after a long walk. Boredom on a highway, jet lag after an overnight flight. These distances are tied to memories, to how your body feels, to things you've actually done. You could call all of these human-scale distances. Our ancestors didn't need to cross galaxies. They needed to cross valleys, rivers, and plains. They needed to know how far it was to the next water source, how long it would take to reach a hunting ground, how many days of walking separated one camp from another. Over tens of thousands of years, our brains became very good at this. At judging a distance we can walk in a few minutes, a few hours, maybe a few days. Even our tools for measuring distance grew out of that same experience. Meters, kilometers, miles, they're all ultimately based on the size of our planet and the way we move across its surface. They work beautifully at that scale. If someone tells you a city is 500 kilometers away, you may not picture every meter. But that's a long drive, maybe half a day in the car. It means something. Up to a point, kilometers and miles let us keep our intuition. They keep distances anchored to our bodies, our vehicles, our sense of time. But that point is much closer than you might think. As soon as we step off our planet and start asking, how far is it to the moon? To the sun? To the next star? Those same units that feel so natural on Earth begin to fail us. The numbers get so large that they stop connecting to anything we've personally felt. 100 kilometers, 1,000 kilometers, 10,000 fine. But 100 million? A trillion? Our inner map starts to dissolve. And that is exactly where the light year comes in. Before we can appreciate why astronomers needed such a strange-sounding unit, and why they built it on the speed of light, We need to push just a little bit beyond these comfortable human-scale distances and see where our everyday measurements start to break. To understand a light year, we first have to watch our familiar units fall apart. Now let's take one careful step off the surface of Earth. The first real distance that pushes us beyond our comfort zone is the gap between Earth and the Moon. On paper, the average distance is about 384,000 kilometers. That's a simple number to write, but try to actually picture it. It's not like driving from one side of a continent to the other. There's no road that winds through hills and cities. There are no mountains or oceans in between. From Earth to the Moon, there is just emptiness. No air, no landmarks, no scenery. Only hundreds of thousands of kilometers of black space. Even the phrase 384,000 kilometers doesn't connect to anything we've personally done. You can imagine driving a few hundred kilometers. You might have flown a few thousand, but hundreds of thousands. The only way to make it feel a little more real is to tie it to time and speed. When NASA sent astronauts to the Moon during the Apollo missions, their spacecraft traveled at an average speed of around 11 kilometers per second on the way out. 11 kilometers every second. If you convert that to more familiar units, that's roughly 40,000 kilometers per hour. A commercial jet cruises at about 900 kilometers per hour. That means the Apollo spacecraft were moving more than 40 times faster than a passenger plane. Compared to highway driving, they were going hundreds of times faster than any car you've ever sat in. And yet, even at that unbelievable speed, it still took them about 3 days to reach the Moon. 3 days of continuous motion, rocketing through space at 40,000 kilometers an hour, just to get to the nearest celestial body in the sky. The one you can see with your naked eye. The one that feels close enough to touch. If it takes 3 days at those speeds to reach something that close, what happens when we look a little farther? Let's aim for the Sun. The average distance from Earth to the Sun is about 150 million kilometers. We can write that as 150 million kilometers, or 150 million kilometers. But unless you already think in millions, your brain probably just hears a really big number and stops there. There's no natural hook. You've never traveled a million of anything, let alone 150 million. So again, we tie it to speed and time. Take that Apollo speed of roughly 11 kilometers per second. If you could point the Apollo spacecraft straight at where the Sun appears to be and somehow keep it from melting, how long would it take to cover 150 million kilometers? At 11 kilometers every second, you'd need on the order of 5 months of continuous travel to reach the Sun's distance from Earth. 5 months of moving faster than any human has ever moved on a planet's surface, without ever slowing down, just to cover that gap. Now think about the fastest spacecraft humanity has ever flown, NASA's Parker Solar Probe. Near its closest approaches to the Sun, it reaches speeds of about 192 kilometers per second. That's around 700,000 kilometers per hour. At that speed, you could go from New York to Los Angeles in less than 30 seconds. You could circle Earth in a little over a minute. It is, by any everyday standard, unimaginably fast. And yet, even the Parker Solar Probe still takes months to complete its highly elliptical orbits around the Sun months, at a speed that turns our normal ideas about motion into a joke, just to move around inside our own solar system. These examples reveal something important. Kilometers work beautifully on Earth. They work okay for the distance to the Moon. But very quickly, as we move outward, they stop behaving like distances and start behaving like raw numbers. You can say 384,000 kilometers for the Moon. You can say 150 million kilometers for the Sun. You can say 40 trillion kilometers for the nearest star. But each time you add another few zeros, your intuition drops one step further behind. There's no feeling attached to those numbers anymore. Your brain can't link them to a journey you've made, to muscles you've used, to hours you've watched tick by on a clock. They become, in a very real sense, symbols on a page. You can do math with them. You can plug them into equations. Engineers and computers can handle them just fine. But as a human being, you no longer feel the difference between 1,000,000 kilometers and 1 billion, between 10 billion and 1 trillion. They all just register as huge. It's as if someone told you the distance between two cities in millimeters. Technically, the number would be correct, but it would be so big, so unwieldy, that it would be almost useless for building any real sense of how far apart those cities are. That is exactly what happens when we insist on using kilometers and miles to talk about the universe. Between planets, between stars, between galaxies, the numbers explode so quickly that even a scientist's brain can't hold them as anything more than abstract quantities. The scale of space isn't just large, it's qualitatively different from the world we evolved in. So astronomers did something clever. They stopped trying to stretch our everyday units farther and farther. Instead, they built a new unit on top of something deeper and more fundamental than Earth, cars, or airplanes. They built it on light itself, on the one speed in the universe that never changes, no matter where you are or how fast you're moving. Astronomers needed a new way to talk about these distances, something tied to the most fundamental speed in the universe. So what exactly is a light year? Let's clear up the biggest misunderstanding right away. A light year is not a measure of time. It sounds like it should be, because it has the word year in it, but it isn't. A light year is a measure of distance. Specifically, it's the distance that light travels in the vacuum of space in 1 year. That's all. 1 light year equals how far a beam of light gets if you let it run for a full year. So why build a unit around light? Because light is special in a way almost nothing else is. Light is the fastest thing in the universe. According to everything we know about physics, nothing, not rockets, not particles, not information itself, can move faster than light through space. This isn't just a technological problem, like, we haven't built a fast enough engine yet. It's a law of nature woven into the way space and time behave. And unlike cars, planes, or even planets, light speed doesn't depend on where you are or what you're doing. The speed of light in a vacuum is a constant of nature. It's the same here on Earth, out near Pluto, in the center of our galaxy, or at the very edge of the observable universe. We usually write this special speed with a single letter, c. Its exact value is about 299,792.458 kilometers per second. For our purposes, we'll round it to 300,000 kilometers per second. The difference doesn't matter for the kind of intuition we're trying to build. That number is so big that it's easy to let your eyes slide over it. So let's slow it down and see what it really means. Every second, light travels 300,000 kilometers. In the time it takes you to snap your fingers, light has already gone 300,000 kilometers. In the time it takes you to blink, it's gone even farther. If you could somehow trap a beam of light at Earth's equator and let it race around the planet, it could circle the entire world about 7.5 times in a single second. Think about that. Around the world, not once, but 7 times, before you could even say the word one. If you drew a straight line from Los Angeles to New York and asked light to run that route, it could go there and back dozens of times in 1 second. A journey that takes you hours on a plane would be over so quickly for light that, from its perspective, there almost isn't a journey. Compare that to things we're familiar with. A commercial jet flies at around 900 kilometers per hour. That's only about 0.25 kilometers per second. Light is roughly 1,000,000 times faster. One of the fastest cars ever built has reached around 1,200 kilometers per hour, about 0.33 kilometers per second. Light is close to 900,000 times faster. Even the Parker Solar Probe, the fastest spacecraft humans have ever launched, reaches about 192 kilometers per second near the Sun. That sounds huge, until you realize light is still more than 1,500 times faster. At human scales, these differences are almost impossible to imagine. But they matter because even at this incredible speed, light still takes time to travel. We already saw a hint of that. From the moon to Earth, light needs about 1.3 seconds. When astronauts spoke to mission control during the Apollo missions, their words, carried as radio waves traveling at light speed, took 1.3 seconds to get here and 1.3 seconds to get back. Every sentence had a built-in pause. From the sun to Earth, light needs about 8 minutes and 20 seconds. The sunlight warming your face right now left the sun more than 8 minutes ago. If the sun could magically vanish this instant, we wouldn't see it disappear or feel the change until those 8 minutes had passed. That's how fast 300,000 kilometers per second really is. Unimaginably quick at our scale, but not instantaneous on the scale of the solar system. For a long time, people didn't realize this. It was natural to assume that light must move infinitely fast. You open your eyes, and the world is just there. There's no visible delay. Feels instant. The first real clue that light has a finite speed came in the 1670s from a Danish astronomer named Ole Romer. Romer was observing the moons of Jupiter, watching them pass in and out of Jupiter's shadow. These eclipses happen on a regular schedule, like a clock. But Romer noticed something odd. Sometimes the eclipses happened a little earlier than predicted, sometimes a little later. The difference turned out to depend on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses seemed to happen early. When Earth was farther away, they seemed late. Romer realized the eclipses themselves were perfectly regular. The light from those eclipses, however, had to travel different distances to reach Earth as our planet moved along its orbit. The extra distance meant extra travel time. From that delay, he could estimate how fast light must be moving. His numbers weren't perfect. Astronomers at the time didn't yet know the exact size of Earth's orbit, but the idea was revolutionary. Light doesn't get from place to place instantly. It has a speed, a very high speed but a finite one. Over the centuries since Romer, we've measured that speed with incredible precision using lasers, mirrors, and atomic clocks. Every experiment tells us the same thing. In a vacuum, light always moves at exactly the same speed. It doesn't matter what direction you're going or how fast you're already moving. That constancy, the fact that light's speed is fixed and universal, is what makes it such a powerful foundation for a unit of distance. If you know how fast light moves and you know how long it's been moving, you can work out how far it has gone. And that finally brings us back to the light year. Take this unchanging speed, about 300,000 kilometers every second. Let it run for 1 full year, every second of every day. The total distance you get at the end of that year is 1 light year. In the next section, we'll turn that into an actual number, and then we'll try to make that number mean something. We've talked about the speed of light. Now we need to talk about something our brains are much worse at: how big the number gets when you let that speed run for a whole year. Before we even say light year, we have to get comfortable with a different word, trillion. We hear million, billion, and trillion all the time, in news stories about money, in budgets, in populations. They all sound like very big numbers. And because they're all big, we tend to lump them together in our heads. But they are not even close to each other. To feel that difference, it helps to measure them not in money, but in seconds, because seconds are something we all understand. Imagine you start counting right now. 1, 2, 3, and you keep going one number every second without stopping. No sleep, no breaks, no days off. How long would it take to reach 1 million? 1 million seconds is about 11.5 days. Not even 2 weeks. You could imagine that. People go on trips that long. Students wait that long for exams. 2 weeks is within the range of, I can picture my life over that time. Now let's jump to 1 billion seconds. A billion is 1,000 millions. So if a million seconds is about 11.5 days, a billion seconds is 1,000 times that. 1 billion seconds is roughly 32 years. Think about that jump. 11.5 days to 32 years. If you started counting seconds when you were born and somehow never stopped, never slept, never paused, you'd reach 1 billion at about your 32nd birthday. A million seconds is a short vacation. A billion seconds is a full adult generation. Now let's try 1 trillion. A trillion is 1,000 billions. So we multiply that 32 years by 1,000. 1 trillion seconds is about 31,700 years. That number is so large it slips out of ordinary history and into prehistory. 31,700 years ago, the last ice age was still in full swing. Vast ice sheets covered large parts of North America and Eurasia. There were no cities, no writing, no agriculture. Humans lived in small bands of hunter-gatherers, using stone tools, following herds, painting on cave walls. If someone had started counting 1, 2, 3. Back then, one number every second non-stop through the end of the Ice Age, through the rise of agriculture, through the building of the pyramids, through the Roman Empire, through the entire span of recorded history, through the Industrial Revolution, through everything that has ever happened in human civilization, they would still not be finished. They'd still be counting today, and they'd still have years left to go before they reached 1 trillion. That's the difference between a billion and a trillion. A million seconds, about 11.5 days. A billion seconds, about 32 years. A trillion seconds, about 31,700 years. Each step up isn't just a bit more. Each step is 1,000 times more than the one before. Now keep that feeling in mind, because when we talk about a light year, we're about to use that word trillion in a very serious way. We said that light travels about 300,000 kilometers every second. If you let it run for 1 full year, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year, and you multiply all of that together, you get a total distance of about 9.46 trillion kilometers. That's 1 light year, not a stretch of time, a distance. 9.46 trillion kilometers that light covers while racing through space at 300,000 kilometers every second for an entire year. To make that more concrete, remember our earlier walk. At a normal pace, you might walk 1 kilometer in about 10 to 12 minutes. Think about the walk from your home to a nearby store or bus stop. That's roughly a kilometer. Your legs understand that distance. Your body has felt it. Now imagine lining up those 1 kilometer walks end to end. 1 kilometer, then another, then another. If you walked 1 kilometer, sat down, teleported to the end of that kilometer and walked another, and repeated that process 9.46 trillion times, you would have walked a light year. Every single one of those kilometers is the kind of distance you could cover on foot in a short stroll, and there are 9.46 trillion of them in just 1 light year. It's such an enormous number that, for our brains, it might as well be infinity. We can say it. We can write it down. We can punch it into calculators and use it in equations. But we cannot feel it in the same way we feel a 10-minute walk or a 2-hour drive or even a 15-hour flight. Somewhere between a million and a billion and a trillion, our intuition drops out. The numbers keep going, but our ability to imagine them doesn't. That's important to remember as we go on. When astronomers say a star is 10 light years away, or a galaxy is millions of light years distant, they're talking about distances that involve trillions and quadrillions of kilometers. Distances so large that the word kilometer stops being helpful at all. Our minds weren't built for numbers this big. At a certain point, they stop being quantities we can picture and become more like symbols that tell us, simply, this is far beyond anything you've ever experienced. So instead of trying to picture every kilometer, we use the light year as a kind of shortcut. A way of saying, take the fastest thing in the universe, let it run flat out for this long, and that is how far away this object is. In the next part of this journey, we're going to climb a ladder built from light itself. Light seconds, light minutes, light hours, light days, all the way up to light years. And at each step, we'll pin that abstract unit to something real in our solar system, so that trillions of kilometers start to have shapes and stories attached to them. We've seen how big the number gets when light runs for an entire year. Now let's work our way up to that slowly, one step at a time, using smaller units built from the same idea. We'll start with the simplest one, the light second. Light travels about 300,000 kilometers in 1 second. So, 1 light second equals 300,000 kilometers. That's already an enormous distance by human standards. In 1 second, light goes farther than a commercial jet could in many hours. To see what that means in a real situation, let's go back to the moon. The average distance from Earth to the moon is about 384,000 kilometers. If 1 light second is 300,000 kilometers, then Earth-Moon distance is almost equal to 1.3 light seconds. That means when light or a radio signal leaves Earth and heads for the moon, it takes about 1.3 seconds to arrive. When it leaves the moon and heads back to Earth, it takes another 1.3 seconds. You can hear this delay in recordings from the Apollo missions. An astronaut speaks on the moon. Mission control in Houston doesn't hear it until about 1.3 seconds later. They reply. The astronaut doesn't hear that reply until 1.3 seconds after it's sent. Every single exchange has an almost 3-second round-trip lag baked in, just from the finite speed of light. It's subtle, but it's always there. The universe reminding us that information has to cross real distances, and that those distances take time. Now let's scale up to the next step on the ladder. 1 light minute equals 60 light seconds. If 1 light second is 300,000 kilometers, then 1 light minute equals 300,000 kilometers times 60 is almost equal to 18 million kilometers. 18 million kilometers in just 60 seconds. What can we attach that to? This is where Mars becomes useful. Mars and Earth orbit the Sun at different distances and at different speeds, so the distance between them is constantly changing. Sometimes they're relatively close on the same side of the Sun. Sometimes they're on opposite sides much farther apart. At their closest, Earth and Mars are about 32 million kilometers apart. That's roughly 2 light minutes. At their farthest, when they're on opposite sides of the Sun, the distance can be around 400 million kilometers, which is approximately 22 light minutes. That range, 2 to 22 light minutes, is the reality NASA has to deal with when operating rovers on Mars. Every command sent from Earth travels at the speed of light. So does every signal sent back by the rover. That means, at best, there's a 4-minute round-trip communication delay. At worst, there's a 44-minute round-trip delay. You can't drive a Mars rover the way you drive a remote control car. If you turned the wheel and waited for the rover to respond in real time, you'd crash it into a rock long before the signal ever arrived. Instead, engineers send carefully planned sequences of instructions, then wait. They look at the data that comes back, plan the next move, send new commands, and wait again. The finite speed of light, those few stubborn light minutes, dictates the entire rhythm of the mission. All of that complexity comes directly from that simple number. 1 light minute is almost equal to 18 million kilometers. Let's climb one more step. 1 light hour equals 60 light minutes. So if 1 light minute is about 18 million kilometers, then 1 light hour equals 18 million kilometers times 60 is almost equal to 1.08 billion kilometers. Over 1 billion kilometers in a single hour of travel at light speed. Now we're far beyond the inner solar system, out where the giant planets live. At its closest approach to Earth, the planet Saturn is roughly this kind of distance away, on the order of 1 to 1 and a bit light hours. Not exactly, because orbits are complicated and always changing, but close enough for our intuition. For more than a decade, the Cassini spacecraft orbited Saturn, sending back some of the most detailed images we've ever seen of that planet and its rings and moons. Each picture it took, each packet of data it transmitted, had to cross that billion-kilometer gulf between Saturn and Earth. Those signals, traveling at the speed of light, took over an hour to arrive. Imagine what that means from the perspective of someone working on the mission. You design a sequence of observations. Cassini executes them near Saturn, takes a photo of the rings, or measures the atmosphere of Titan, one of Saturn's moons. Then it beams the data home at light speed. You don't see anything for an hour or more. From the moment the camera shutter closes to the moment the image appears on a screen in a NASA control room, more than 60 minutes pass, simply because the universe is big enough that even light needs that long to cross it. By the time you're looking at the picture, it's already over an hour old. You'll notice a pattern here. At 1 light second, we felt a small but noticeable delay between the Earth and the Moon. At light minutes, controlling robots on Mars became a slow, careful process of plan, send, wait. At light hours, even the most basic data from Saturn arrives on a significant delay. These aren't thought experiments. They aren't abstract possibilities. They are built into the way we actually explore the solar system. Engineers designing missions have to account for light seconds, light minutes, and light hours in every plan they write, every maneuver they schedule, every emergency procedure they design. The speed of light and the distances those light units represent is not optional. It sits at the core of everything we do beyond Earth. And we haven't even reached a single light day yet. We've only climbed from seconds to minutes to hours, just like we do with time in our daily lives. But by tying each step to a real example, a moon conversation, a Mars rover, a Saturn probe, we've started to turn the idea of light distance into something we can feel, not just recite. Next, we're going to keep climbing. From light hours to light days, light weeks, light months, and finally to a full light year. And we'll see where our fastest spacecraft are on that vast, glowing ruler of space. We've climbed from light seconds to light minutes to light hours. Now let's keep going. If 1 light hour is about 1.08 billion kilometers, then the next natural step is the light day. 1 light day equals 24 light hours. So we take that 1.08 billion kilometers and multiply by 24. 1.08 billion kilometers times 24 almost equals 25.9 billion kilometers. That's the distance light covers in a single day. Even at the speeds we've talked about, Apollo, Mars probes, Cassini, 25.9 billion kilometers is far beyond what anything human-made has covered in a day. But there is one spacecraft that lives roughly on this scale. Voyager 1. Launched in 1977, Voyager 1 has been traveling outward for almost half a century. It flew past Jupiter, then Saturn, then headed for the edge of the solar system. Today, it's the most distant human-made object in existence. Voyager isn't a light day away in terms of distance, it's less than that, but the communication delay to talk to it is now measured in light hours, approaching a full light day there and back. Each radio signal we send from Earth, traveling at light speed, now takes over 20 hours to reach Voyager. Its reply, also at light speed, takes another 20+ hours to come back. A simple ping and pong between us and the spacecraft requires close to a full day of real time. From Voyager's perspective, Earth is now a tiny, faint star in the sky, and home is at least tens of light hours away in terms of total round-trip communication. That's roughly the scale of a light day. A distance so large that even a conversation stretched across it becomes almost meaningless in the way we normally think of talking. Let's keep stretching. If 1 light day is about 25.9 billion kilometers, then 1 light week equals 7 light days. Multiply 25.9 billion kilometers times 7 almost equals 181 billion kilometers. Now we are deep into a region of space where no human spacecraft has ever reached. We're far beyond the orbits of the known planets, beyond even most comets, in the vast, sparse outer reaches of the sun's influence. Out here, at around a light week from the sun, the view would be strange. The sun would no longer dominate the sky the way it does from Earth. It wouldn't be a blinding disk filling your vision. Instead, it would begin to look more like a very bright star. Still clearly the main source of light, but no longer an overwhelming presence. The planets we know, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, would all be huddled close to that point of light, so close together that to the naked eye they'd almost blend into the sun's glare. Our entire planetary system, everything we've ever visited with probes, would be compressed into a tiny clump around that bright star. At a light week, you're still very much inside the sun's gravitational reach, but psychologically, you've left the planetary neighborhood. You're in deep space. We can go further. If one light week is roughly 181 billion kilometers, then a rough light month, not a precise calendar month, but about 30 days of light travel is, one light month is almost equal to 30 light days. So, 25.9 billion kilometers times 30 almost equals 778 billion kilometers. Nearly 800 billion kilometers in every direction. At this distance, if you could look back at the solar system with a decent telescope, the sun would absolutely be just another bright star. The planets would be invisible to the naked eye, lost completely in that star's light. Even with a powerful telescope, Jupiter might be a faint dot. Earth, Mars, Saturn, everything we think of as familiar territory would be hidden right up against that bright pinprick. Everything we know, all of human history, every spacecraft, every life form we are aware of would fit into a region of space so small that, from a light month away, it would be a single sparkling point. Remember what these numbers mean. In 1 second, light travels 300,000 kilometers. In 1 minute, about 18 million. In 1 hour, over a billion. In 1 day, about 25.9 billion. In 1 week, about 181 billion. In 1 month, about 778 billion. Each step multiplies the distance by another familiar time unit. Just like we stack seconds into minutes, minutes into hours, hours into days, days into weeks and months, we're stacking light seconds into light minutes, into light hours, into light days and beyond. Now we're finally ready to see what happens when we stack them for a full year. Let's do the multiplication once. Slowly. Start with the speed of light. 300,000 kilometers per second. There are 60 seconds in a minute. 300,000 times 60 is equal to 18 million kilometers per minute. 60 minutes in an hour. 18 million times 60 almost equals 1,080,000,000 kilometers per hour. 24 hours in a day. 1,080,000,000 times 24 almost equals 25,920,000,000 kilometers per day. 365 days in a year. 25,920,000,000 times 365 almost equals 9,460,000,000,000 kilometers. Written out, that's greater than 9,460,000,000,000 kilometers, which we usually shorten to greater than 9.46 trillion kilometers. That is 1 light year, the distance light travels in the vacuum of space. At 300,000 kilometers every second, 460 seconds per minute, 60 minutes per hour, 24 hours per day, 365 days in a row. When astronomers say that a star is 10 light years away, they mean 10 times 9.46 trillion kilometers. When they say that our galaxy is about 100,000 light years across, they mean 100,000 times that distance. Kilometers simply can't handle these scales without collapsing into unreadable walls of zeros. But light years give us a unit that's still enormous, but at least manageable. A unit that ties together distance and time in a way that's deeply physical. Because each light year is not just a lot of kilometers. It's how long light had to travel, how much time passed while it was on the way, how far into the past we are looking when that light finally reaches us. This distance, the 1 year's worth of travel at the ultimate speed limit of the universe, is the basic ruler we use to measure the space between stars. From here on, when we talk about other suns, about our place in the Milky Way, and about the structure of the universe itself, light years will be the language we use. Now that we have a sense of what a light year is, let's point that ruler at something specific. The obvious place to start is with the nearest star beyond our sun. That star is called Proxima Centauri. Proxima is part of a small triple star system known as Alpha Centauri, about 4¼ light years away. Two of the stars in that system, Alpha Centauri A and B, are somewhat similar to our sun, orbiting each other in a slow, graceful dance. Proxima is the third member, a small, faint red dwarf star that orbits much farther out. Red dwarfs are the most common type of star in our galaxy. They're smaller and cooler than the sun, burning their fuel so slowly that they can live for trillions of years. But they're also so dim that you can't see Proxima with the naked eye, even though it's our closest stellar neighbor. In other words, the nearest star beyond the sun is too faint to see without a telescope and still 4.24 light years away. In kilometers, that's roughly greater than 40 trillion kilometers. 40 trillion kilometers. Remember how huge a trillion is. Remember our counting game. A million seconds, 11.5 days. A billion seconds, 32 years. A trillion seconds, 31,700 years. Now imagine 40 trillion kilometers of space between us and Proxima Centauri. It's easy to hear 4.24 light years and think, well, that doesn't sound too bad. It's only 4 of something. But each one of those 4 is 9.46 trillion kilometers long. The true scale is hidden inside the unit. To make that distance a bit more real, let's ask a simple, brutal question. If we launched our fastest spacecraft straight at Proxima Centauri today, how long would it take to get there? The current speed champion is, again, the Parker Solar Probe, which can reach about 192 kilometers per second near the Sun. That's more than 1,500 times faster than a typical commercial jet. If you could somehow keep Parker at that peak speed, in a straight line toward Proxima Centauri, it would still take on the order of 6,800 years to arrive. 6,800 years. To put that in perspective, written language was only invented about 5,000 years ago. The pyramids of Egypt are around 4,500 years old. Recorded human history, as we usually define it, is younger than the hypothetical journey time to Proxima at our fastest current speeds. You could have launched such a mission when humans first started writing on clay tablets, and it still wouldn't have arrived yet. Civilizations would rise and fall, languages would be born and die, entire cultures would vanish before the spacecraft ever reached its target. That's where 4.24 light years stops being just a neat number and becomes a wall. But what if we go far beyond rocket technology as we know it? What if we take a concept that pushes our current engineering to the absolute edge? One of the most serious proposals is called Breakthrough Starshot. The idea, announced in 2016, is simple to describe and extremely hard to do. Build a tiny spacecraft weighing only a few grams, basically a computer chip with a camera and some sensors, attached to an ultra-thin reflective sail. Aim a gigantic array of ground-based lasers at that sail. Use the pressure of light, yes, light really can push on things, to accelerate the craft to about 20% of the speed of light. At 20% light speed, or about 60,000 kilometers per second, the numbers change dramatically. Instead of 6,800 years, a trip to Proxima Centauri would take roughly 20 years of travel time, plus about 4 years for the data signal to come back to Earth at light speed. So, in principle, you could launch a probe and receive its pictures and measurements from the Proxima system within a single human lifetime. maybe 24 to 25 years after launch. On paper, that sounds almost magical compared to thousands of years. But the devil is in the engineering. To accelerate a gram-scale spacecraft to 20% of light speed, you need a laser array with a total power on the order of 100 gigawatts or more. That's roughly comparable to the output of 100 large nuclear power plants, all focused into a narrow beam, pointed precisely at a sail only a few meters across, thousands of kilometers away. The beam has to remain locked on that tiny sail as it accelerates for minutes, long enough to push it to the required speed. Any misalignment, and the sail drifts out of the beam and stops accelerating. Then there's the journey itself. At 60,000 kilometers per second, even tiny dust grains in space become dangerous. A grain of dust smaller than a sand particle hitting the spacecraft at that speed would release as much energy as a large explosive. Yet you can't surround the craft with heavy shielding. That would weigh it down and make it impossible to accelerate with light pressure. You need a design that's both robust enough to survive high-energy impacts and light enough to be pushed by laser light, two requirements that pull in opposite directions. And even if you reach Proxima Centauri in 20 years, there's another problem. You can't really slow down. The Starshot concept assumes a one-way flyby. The probe would zip past Proxima and any planets it might have in a matter of hours, maybe days at most. All of the observations would need to be made in that short window, at insane closing speeds with no chance to stop in orbit or turn around. Then comes communication. A craft the size of a postage stamp or a coin can't carry a powerful transmitter or a big antenna. Yet it would have to send data back across 4.24 light-years, about 40 trillion kilometers, using only milliwatts of power. By the time that whisper of a signal arrives at Earth, it will have spread out into a giant sphere of radio waves, unimaginably faint. We would need extremely large, sensitive receiving arrays on Earth, very clever encoding and error correction schemes, a lot of patience, all for a handful of images and a few streams of data from a probe that flashed past its target in a heartbeat and then disappeared into the dark forever. Breakthrough Starshot is a brilliant concept. It's based on real physics, not science fiction. But it's also a reminder of just how demanding our universe is when you try to cross light-year distances, even with revolutionary ideas. And remember, Proxima Centauri is not a special case. It isn't on the far side of the galaxy. It isn't in another cluster or another universe. It is simply the closest star we have, the very first stepping stone beyond the sun. And still, at our current fastest speeds, thousands of years, with an extreme, not yet built laser sail system, decades plus years more for the reply, no stopping, no rescue, no second chances. When you fold all of this together, for 0.24 light-years stops sounding modest. It starts to reveal its true character, not as a manageable gap, but as a chasm. Even our closest stellar neighbor is, for now, almost completely out of reach. And that is just 4 light-years. In the next part of this journey, we'll see how those light-years also act as a kind of time machine, letting us look backwards into the history of the universe every time we look up at the night sky. We've been treating the light year as a unit of distance, a way of saying how far away something is. But because light has a finite speed, every light year of distance also means a certain amount of time. That means every time you look out into space, you're not just looking far away. You're looking backwards. We've already met this idea in the solar system. Light from the moon takes about 1.3 seconds to reach us. Light from the sun takes about 8 minutes and 20 seconds. So when you glance up at the moon, you're not seeing it exactly as it is right now. You're seeing it as it was 1.3 seconds ago. Not a huge delay, but still a delay. If something dramatic happened on the moon, say a giant meteor impact, you wouldn't see the flash until more than a second after it happened. With the sun, the effect is bigger. When you see the sun shining in a blue sky, you're seeing it as it was 8 minutes and 20 seconds in the past. If the sun could somehow vanish this instant, the sky would remain bright for over 8 more minutes. The warmth on your skin would keep arriving for those 8 extra minutes. For that period of time, the sun would be gone, but its light would still be on the way. That's what the finite speed of light really means. There is always a gap between when something happens and when you get the news. Now let's carry this idea out to the stars. Take Sirius, the brightest star in the night sky, in the constellation Canis Major. Sirius is about 8.6 light-years away. That number tells us 2 things at once. Sirius is far away. Light has to travel 8.6 light-years of distance. The light we see tonight spent 8.6 years crossing that distance. So when you look at Sirius, you are seeing it as it was 8.6 years ago. If you're 20 years old, you see Sirius as it was when you were about 11. If you're 40, you see it as it was in your early 30s. In day-to-day life, 8.6 years is a major chunk of time. You might start and finish school in that period, or change careers, or watch a child grow from a toddler to a teenager. Yet from the point of view of Sirius, you are always seeing it with that built-in delay. You never see its true present. Now think about Vega, one of the brightest stars in the summer sky. Vega is about 25 light-years away. That means the light entering your eyes tonight left Vega 25 years ago. If you're 25 years old, the light you see from Vega started its journey the year you were born. When those photons left the star, you didn't exist yet. Your parents might have been your age now or younger. The world's politics, technology, and culture were different. If you're older, the light left even further back in your personal timeline. The star you're looking at tonight is showing you its state a quarter of a century ago, not as it is in this instant. We can push this idea further to truly staggering time offsets. Consider Betelgeuse, the bright red star marking the shoulder of Orion. Betelgeuse is about 550 light-years away. 550 years. The light from Betelgeuse that you see on a clear winter night left that star sometime around the year 1474. To put that in human terms, it was the time of the Renaissance in Europe. Leonardo da Vinci was a young man in his 20s. Michelangelo hadn't yet begun his major works. Columbus had not yet sailed to the Americas. The printing press was still a relatively new technology. Everything that has happened in human history since then, from the age of exploration through the Industrial Revolution, through the World Wars, through the entire digital age, has unfolded while those photons were quietly crossing the 550 light-years of space between Betelgeuse and Earth. Tonight, they finally arrive and end their journey in your eyes. And here's the unsettling part. Betelgeuse is a massive, unstable star nearing the end of its life. At some point, astronomically soon, within the next 100,000 years or so, it will explode as a supernova. It might not have exploded yet. It might not explode for tens of thousands of years. But it's also entirely possible that it already has. Betelgeuse might have detonated centuries ago. The explosion could have occurred in the 1600s while Galileo was pointing his first telescope at the sky, or in the 1700s while the world was changing under the Enlightenment, or in the 1800s as the first photographs were being taken. If it did, we wouldn't know. We would still see Betelgeuse shining calmly in the sky, because the light from that catastrophe hasn't reached us yet. The update about its death is still in transit. For up to 550 years after the event, we would continue to see an intact star, even though, in reality, it was already gone. In that sense, a star like Betelgeuse can be a kind of ghost in the sky, a picture from the past of something that no longer exists in the present. The same is true on slightly shorter timescales for Polaris, the North Star. Polaris is about 445 light-years away. When the light you see from Polaris tonight began its journey toward us, the early 1600s were just beginning. Shakespeare was alive and writing his later plays. The first permanent English settlements in North America had not yet been founded. the world looked entirely different. The photons entering your eye from Polaris left before the United States existed, before the steam engine, before electricity, before airplanes, before radio, before every piece of technology you're using to watch this video. They have been traveling for more than 4 centuries to find you. Once you start thinking this way, the night sky changes character. Every star becomes a kind of time capsule. Nearby stars, years or decades in the past. Brighter giants, hundreds of years. Distant objects, thousands, millions, even billions of years. You are never seeing the universe as it is right now. You are seeing it as it was, with each object frozen at a different point in its own history, depending on how many light years away it is. If you could somehow turn the entire universe into a giant present tense live stream, no delays, no light travel time, you'd see something completely different from the sky above you. Some of the stars you see now would be gone. Some that looked dim might have brightened. Some that seem perfectly ordinary could have already gone supernova, their last moments still on their way to us across the darkness. But physics doesn't allow that kind of instantaneous view. The finite speed of light makes time and distance inseparable. When we say a star is 10 light years away, we're also saying the star you see is 10 years out of date. When we say a galaxy is 100 million light years away, the light we observe left when dinosaurs still walked the Earth. When we look at the most distant galaxies, the James Webb Space Telescope can see billions of light years away. We're seeing them as they were shortly after the Big Bang, long before our sun existed. Light years are not just a ruler, they're also a timeline laid out in space. Every direction you look, all across the sky, you're peering into different chapters of the universe's past. And Earth, floating here in the present, is surrounded by a glowing, three-dimensional archive of earlier times. That's one of the strangest and most beautiful consequences of living in a universe where light has a speed. You never see the cosmos as it is. You only ever see it as it was some number of light seconds, light minutes, light years, or even billions of years ago. So far, we've talked about individual stars, Sirius, Vega, Betelgeuse, Polaris, as isolated points on our light year ruler. Now let's zoom out a little and look at the neighborhood we actually live in. Imagine drawing a sphere around the sun with a radius of about 20 light years. Inside that invisible bubble, there are hundreds of stars. Not just a handful, hundreds. Some are bright enough to see with the naked eye on a dark night. Most are too faint to notice without a telescope. Many are small, cool red dwarfs that barely glow compared to our sun. Astronomers sometimes call this kind of region our local neighborhood or local bubble. It's a tiny patch of the Milky Way, but it's still a crowded and diverse place. Within these 20 light years, you find sun-like stars, stars a bit bigger or smaller than the sun, fusing hydrogen steadily in their cores. These are the kinds of stars we usually imagine when we think sun. Red dwarfs, much smaller and cooler, often only a fraction of the sun's mass. They burn fuel slowly and can live for trillions of years. They're the most common type of star in the galaxy, but because they're so faint, not one of them is visible to the naked eye from Earth. Binary and multiple star systems, pairs or trios of stars orbiting a common center of mass, like celestial dance partners linked by gravity. White dwarfs, the dense, cooling embers of stars that have finished their main lifetimes, stellar corpses about the size of Earth but with the mass of a star. Each one of these stars sits at its own particular light-year distance from us, which means each one is showing us a different slice of its own past. Take Barnard's star, for example. Barnard's star is about 6 light-years away and is one of the nearest stars after the Alpha Centauri system. It's a small, cool red dwarf, invisible to the naked eye, but famous among astronomers because it moves quickly across our sky relative to background stars. If you took pictures of it a few years apart, you'd actually see it shift position. The light you see from Barnard's star left when the smartphone era was just beginning. It shows us the star as it was 6 years ago. Then there's Wolf 359, around 7.9 light-years away. It's another faint red dwarf, one of the dimmest stars known in our neighborhood. It's much cooler and smaller than the Sun, and again, you need a telescope to see it. Its light shows us what it looked like nearly 8 years in the past. Not all nearby stars are tiny and dim, though. We've already talked about Sirius, 8.6 light-years away, the brightest star in our night sky. Sirius is actually a binary system. Sirius A, a bright white-blue star about twice the mass of the Sun. Sirius B, a tiny white dwarf with the mass of the Sun compressed into a sphere about the size of Earth. They orbit each other every 50 years, each tugging on the other. When you look at Sirius with just your eyes, you're mostly seeing Sirius A, brilliant, dazzling, easily visible from cities. But lurking right next to it is that incredibly dense stellar remnant, glowing white-hot as it slowly cools over billions of years. All of this is happening within just a few dozen light-years of us. The sky you see at night is largely made from these relatively nearby stars, each one glowing with light that started its journey years or decades ago. But stars are only half the story. For a long time, we didn't know whether any of them had planets. Until the early 1990s, the only planetary system we knew of for sure was our own. Astronomers suspected that other stars might have planets, but we had no direct evidence. The first confirmed planets around a Sun-like star were only announced in 1995. Since then, everything has changed. Now we've confirmed thousands of planets around other stars, exoplanets, as they're called. And many of these worlds are surprisingly close in light-year terms. One of the most intriguing systems is called TRAPPIST-1. TRAPPIST-1 is a small, cool red dwarf star about 40 light-years away from us, 10 times farther than Proxima Centauri, but still just down the street on galactic scales. Orbiting this tiny star are 7 rocky planets, all roughly Earth-sized. What makes this system so fascinating is how compact it is. All 7 planets orbit closer to TRAPPIST-1 than Mercury orbits the Sun. 3 of them sit within the habitable zone, where temperatures might allow liquid water on their surfaces, depending on their atmospheres. If you could stand on one of these worlds and look up at the sky, the other planets wouldn't be little specks. Some might appear larger than our moon looks from Earth, huge neighboring worlds hanging in the sky, sweeping close over days instead of months or years. Travel between planets in such a system, at least in principle, would be far easier than travel between planets in our own solar system. The distances are smaller, the orbital periods are short. It almost looks like nature's own compact laboratory for planetary science. But remember the light-year connection. TRAPPIST-1 is 40 light-years away. So, when we look at that system today, we're seeing it as it was 40 years ago. Any signals, radio, laser, anything, sent from there at light speed would take 40 years to reach us. If we responded immediately, our reply would take another 40 years to get back. That's an 80-year round trip for a single message. Send a hello today, receive hello back, when today's children are grandparents. The same is true for any nearby exoplanet system, not just TRAPPIST-1. Within a few tens of light years, there are probably many rocky worlds. Some might be barren, some frozen, some scorched, and some maybe covered in oceans, clouds, or even forests. We don't know yet. Our growing list of confirmed exoplanets is really a list of places measured in light years, worlds whose current state we won't know until the light carrying that information has had time to cross the gulf. So our local stellar neighborhood, this 20, 30, 40 light-year sphere around the Sun, isn't just a cloud of stars. It's a three-dimensional, slowly updating map of other worlds, each one separated from us not just by distance, but by years of light travel time. Some of those stars are sending us light from a time before you were born. Some are sending us light from before your parents were born. Some are sending us light from before your parents were born. Some, like TRAPPIST-1, are only now showing us what they were like in the early 1980s. And all of them, every star, every planet, sit at the very bottom of a much larger structure. Our home galaxy, the Milky Way. In the next section, we'll zoom out again and see what light years look like on that scale. How far it is to the center of the galaxy, how long light has been traveling from there to us, and what it means to live in a system that's 100,000 light years across. So far, light years have been an interesting way to think about distance and time. But if we imagine a future where humans actually try to live at those distances, light years suddenly become something much more serious. They become a limit on how closely we can stay connected. We can already see the beginnings of this just within our own solar system. Take Mars. As we saw earlier, the distance between Earth and Mars changes constantly as both planets move around the Sun. At their closest, signals take about 2 minutes to travel one way at light speed. At their farthest, they can take up to 22 minutes. That means, best case, 4-minute round-trip delay. Worst case, 44-minute round-trip delay. When engineers drive a rover like Curiosity or Perseverance, they don't use a joystick. They can't. If they turned left and waited to see what happened, by the time the rover responded, it might have already hit a rock half an hour ago. Instead, they 1. Receive images sent from Mars hours earlier. 2. Analyze the terrain carefully. 3. Plan a detailed set of commands for the next day. 4. Upload that plan. 5. Wait for the rover to execute it. 6. Get the results back later. Everything is slow, deliberate, and one-directional. The delay forces a completely different style of operation. Now push that farther. The Voyager 1 spacecraft out in interstellar space is so far away that signals now take about 24 hours to reach it. When Mission Control sends a command, they don't hear back until roughly a day later. If something goes wrong, Voyager has to handle it on its own long before engineers even know there's a problem. During the New Horizons flyby of Pluto in 2015, the spacecraft was about 4.5 light hours away. That meant any signal from Earth took 4.5 hours to arrive. Any reply from the spacecraft took another 4.5 hours to come back. There was no way to steer New Horizons live as it flew past Pluto. Every maneuver, every camera exposure, every contingency plan was programmed months in advance. The spacecraft had to carry its own fully scripted choreography and enough autonomy to protect itself if something unexpected happened. These are all examples within a single light day of Earth. Now imagine we someday establish a human colony around Proxima Centauri, 4.24 light years away. Let's pretend we've solved all the impossible engineering problems, starships, life support, shielding, the works, and there's a thriving settlement orbiting a planet around Proxima. What would communication with that colony actually feel like? The numbers are simple. Distance, 4.24 light years. A radio signal or laser beam travels at the speed of light. One-way travel time for a message, 4.24 years. Round-trip time for a question and answer, about 8.5 years. Imagine you're a leader on Earth and you send a message. How is the colony doing? Do you need supplies? Are there any problems? Your signal leaves Earth today. The colonists receive it more than 4 years from now. They discuss it, write a response, and beam it back. You receive their answer over 8 years after you asked the question. Any decision you tried to make based on that information would be hopelessly out of date. The crops they're talking about were harvested years ago. The crisis they describe might already be resolved or might have destroyed the colony entirely. In practical terms, you cannot govern a colony like that from Earth. You can send broad philosophies, founding documents, technical manuals, maybe even occasional high-level suggestions. But you cannot give day-to-day orders. You cannot respond to emergencies. You cannot run a government in any normal sense across a gap of multiple light years. By the time your instructions arrive, the situation will have changed. By the time their reply returns, you might no longer be in power. The government that wrote the message might not even exist. A Proxima colony would have no choice but to be largely autonomous. Earth could be the origin story, the cultural memory, the place of ancestors, but not the place making the rules. Over time, something else would happen too. Culture would drift. Even on Earth, with instantaneous communication by phone and internet, cultures diverge over just a few decades. Slang changes, fashion changes, politics shift, new art forms appear, music evolves. The world of your grandparents already feels like a different country in many ways. Now add an 8-year latency to every conversation. Jokes don't translate across that kind of delay. By the time they arrive, no one is telling them anymore. Political debates are pointless. By the time your argument reaches the other side, the issue might be ancient history. Even shared holidays and events become misaligned. A celebration on Earth might be commemorating something the colony hasn't even heard about yet, because the light carrying that news is still on the way. Messages stop being conversation and start becoming history. A child on Proxima might receive a message from Earth that was sent before they were born. They grow up reading about events that happened right now for the people who wrote the messages, but are already old news by the time they arrive. It's not hard to imagine that, after a few generations, the people of Proxima would think of themselves not as Earthlings who happen to live far away, but as something else. Different slang, different politics, different art and music shaped by a different sky, different values born from life under a red dwarf sun. Earth and Proxima would still be connected, but by letters across decades, not by any kind of shared, living conversation. And Proxima is only 4.24 light-years away. Push the distance farther and the effect becomes extreme. At 10 light-years, a message takes 10 years to go one way, 20 years for a round trip. You could send a question in your 20s and get an answer in your 40s. Parenting, careers, entire phases of life fit inside that delay. At 100 light-years, 100 years one way, 200 years round trip. Here, communication genuinely spans generations. You might send a message as part of a scientific or diplomatic project, knowing that you and your children and probably your grandchildren will never see the reply. The answer will come, if it comes at all, to people who haven't been born yet, in a society that may be completely different from the one that wrote the original question. At that point, interstellar communication stops looking like conversation and starts looking like archaeology or time capsules. Civilizations send out vast summaries of their knowledge, art, and history, hoping that someday, somewhere, someone will receive them. If they get a response at all, it's a message from a different era, written by the distant descendants of whoever first heard their call. Light years limit more than travel. They limit relationships, politics, even the very idea of what it means to share a culture. This doesn't mean human colonies around other stars are impossible. But it does mean that if they exist, they will almost certainly be independent worlds, not provinces of a central galactic empire controlled from Earth. Each colony would have its own timeline, its own decisions, its own future, linked to Earth by thin, slow threads of light, carrying memories from one world to another across the centuries. In the next part of our journey, we'll zoom even farther out and see how light years shape not just our local neighborhoods and hypothetical colonies, but our entire galaxy, and what it means to live inside a structure that is itself hundreds of thousands of light years across. Up to this point, we've mostly treated the speed of light as a very large number, 300,000 kilometers per second, and used it to define distances. But there's a deeper reason the light year is so important. It isn't just that light is fast. It's that nothing can go faster. And that isn't an engineering problem. It's not something we can fix with better rockets or more advanced engines. It's built into the way space and time themselves work. To see why, we have to compare the universe we think we live in with the universe we actually inhabit. In everyday life, speeds add in a simple, intuitive way. If you're on a train moving at 50 kilometers per hour and you throw a ball forward inside the carriage at 20 kilometers per hour relative to you, someone standing on the ground will see the ball moving at about 50 kilometers per hour, train, plus 20 kilometers per hour, throw, equals 70 kilometers per hour. Your speed plus the ball's speed. This rule feels obvious. It works for cars, planes, boats. It's built into our intuition. It's so natural that, for a long time, people assumed it must also hold at any speed, including the speed of light. Now imagine a spacecraft drifting through space at half the speed of light, 0.5 c. Inside the ship, an astronaut turns on a flashlight, shining a beam straight ahead. You might expect that, to someone watching from outside, the light from the flashlight should be moving at 0.5 c, spacecraft, plus 1.0 c, light relative to the ship, equals 1.5 c, 1.5 times the speed of light. But that is not what happens. No matter who measures it, the astronaut on the ship measures the light from their flashlight traveling at c. An observer outside, watching the ship zoom past at 0.5 c, also measures that flashlight beam traveling at c. A third observer, moving in some completely different direction, measures the same c. Everyone, in every situation, always gets the same number for the speed of light in a vacuum. Something has to give. If light speed is always the same while your speed can change, then the universe cannot let you keep adding speeds in the simple train plus ball way when you get close to light speed. Instead, the universe bends something else to make the numbers work out. What bends is space and time themselves. Einstein's theory of special relativity, published in 1905, showed that if the speed of light is constant for all observers, then time cannot tick at the same rate for everyone. Lengths cannot be the same for everyone. Events that look simultaneous from one point of view may not be simultaneous from another. Two key effects emerge. 1. Time dilation. Time runs more slowly for an object that is moving very fast, as seen from a stationary observer. 2. Length contraction. Distances along the direction of motion appear shorter to the moving object compared to what a stationary observer measures. These are not illusions. They are real physical effects, and we've measured them over and over again. Here's one way we know. Consider particles in a particle accelerator like those at CERN. Many of these particles are unstable. They naturally decay into other particles after a very short lifetime. When those particles are at rest in a laboratory, we can measure how long they live before decaying. That gives us their proper lifetime. But when we accelerate them to speeds close to the speed of light, something strange happens. They live longer. From our point of view, watching from the lab, the fast-moving particles take more time to decay than identical particles at rest. It's not because we measured wrong. It's because time is literally passing more slowly for the particles as they move at those speeds. Their internal clocks, the processes that lead to their decay, are slowed down relative to us. Another example comes from nature itself. Muons created high in Earth's atmosphere. Muons are produced when cosmic rays from space slam into molecules in the upper atmosphere. Muons are unstable. At rest, their half-life is so short, about 2 microseconds, that even moving at near light speed, they shouldn't be able to travel far enough to reach the ground before decaying. Yet, when we put detectors at the surface, we find plenty of muons making it all the way down to us. Why? From our perspective, the muons are moving so fast that time dilation stretches their lifetimes. They live long enough to cover the distance. From the muon's own perspective, its lifetime is perfectly normal, but the atmosphere it has to cross is length contracted, squashed into a much shorter thickness along its direction of motion. Two observers, two views of reality, but the same physical outcome. Then there's a piece of technology you might use every day without realizing it depends on relativity. GPS. GPS satellites orbit Earth at high speeds and at altitudes where Earth's gravity is slightly weaker than at the surface. Both their motion and the weaker gravity affect the rate at which time passes for them. Because they're moving, special relativity says their clocks should run a bit slower than identical clocks on Earth. Because they're higher up in a weaker gravitational field, general relativity, Einstein's other great theory, says their clocks should run a bit faster than clocks on the ground. We can calculate both effects. When we do, we find that the net result is that clocks on GPS satellites tick faster than clocks on Earth by about 38 microseconds per day. That sounds tiny, but if engineers didn't correct for it, GPS positions would drift by several kilometers every day. Your phone would show you miles away from where you actually are. The fact that GPS works as well as it does is direct, practical proof that time dilation is real. All of this is leading to a crucial point. As you push an object closer and closer to the speed of light, time for that object, as seen from the outside, slows down more and more. Its effective inertia, its resistance to acceleration, increases. It becomes harder and harder to speed it up further. The equations of relativity show that the amount of energy needed to keep accelerating a massive object rises sharply as you approach light speed. At everyday speeds, this extra energy is negligible. Newton's simple laws work fine. But as you get close to C, the curve steepens. To go from 90% of light speed to 99% takes a huge amount of additional energy. To go from 99% to 99.9% takes far, far more. And to reach 100%, the speed of light itself, you would need infinite energy. The universe simply does not have that much energy to give you. That's why, according to all our current understanding, nothing with mass can ever reach the speed of light, let alone exceed it. Photons, the particles of light, are special. They have no rest mass. They are always born already going at c. They don't need to be accelerated to that speed, and they can't slow down below it. Light must travel at light speed. But anything with even the tiniest amount of rest mass is stuck on the slower side of that barrier forever. You can get arbitrarily close to light speed with enough energy, but you can never reach it. There is always another decimal place, another fraction to close, and each fraction costs vastly more energy than the last. So when we look at the night sky and talk about stars that are 10 light years away, or galaxies that are 1,000,000 light years distant, we're not just saying, it would take light this many years to get there. We're also saying, it would take you or any spacecraft you could build at least this many years and probably far, far longer, because you can never travel faster than the light that's already on its way. Naturally, people have wondered if there's some clever way around this. Science fiction is full of warp drives, wormholes, and hyperspace. Tricks that let you effectively outrun light without technically breaking the local speed limit. Some of these ideas have been examined seriously in theoretical physics. For example, the Alcubierre warp drive, proposed in 1994, is a solution to Einstein's equations in which you compress space in front of a spacecraft, expand space behind it. The ship itself, sitting inside a warp bubble, would actually be at rest relative to its local space. It wouldn't be moving faster than light through space. Instead, space itself would be flowing around it, carrying it forward. From the outside, the bubble could appear to move faster than light. It's a clever idea, but there are problems. To create and sustain such a warp bubble, the equations demand a form of exotic matter with negative energy density, something unlike any matter we've ever seen. It's not just rare. As far as our experiments show, it might not exist at all. Even if it does, the amounts required seem ridiculous. Some estimates suggest you'd need more negative energy than exists in the observable universe. There are also deep causality issues. In many warp drive or wormhole scenarios, faster-than-light travel would allow for effective time travel into the past, raising all kinds of paradoxes, kill your grandfather before you reborn type problems that suggest something fundamental would break. Wormholes, another popular concept, suffer from similar issues. In principle, a wormhole is a shortcut through space-time. Enter on one side, exit on the other, having bypassed the distance in between. But any wormhole that stays open long enough to travel through seems to need the same kind of exotic negative energy, again in absurd quantities, and again with potential causality paradoxes. As for hyperspace, an alternate dimension where the rules are different, that's pure speculation. There's no experimental evidence that any such realm exists, let alone that it could be used to cheat the speed of light. At the moment, every realistic, experimentally supported theory we have agrees on one thing. The speed of light is a hard limit in our universe. You can never send a signal, a person, a spaceship, or even a tiny particle faster than light through space without violating the structure of space-time itself. And that brings us back to light years. Light years aren't just big distances. They encode this fundamental speed limit. When we say a planet is 10 light years away, we're not just giving you a huge number. We're also telling you, even in the most optimistic scenario, information cannot get from there to here in less than 10 years. No technology that respects the laws of physics as we understand them can carry you there faster than the light that's already en route. The light year marks not only how far away something is, but also how deeply separated it is from us in time, thanks to a universal speed limit we cannot cross. That's why, when we start measuring things in light years and tens of light years and millions of light years, we're not just talking about size. We're talking about a kind of cosmic separation that may be, in a very real sense, permanent. In the next section, we'll see how that separation plays out on the scale of our entire galaxy, the Milky Way, and what it means to live inside a system that takes hundreds of thousands of years for light itself to cross. So far, we've been wandering around our local neighborhood, a few dozen light years in any direction, the space between us and our nearest stellar neighbors. Now it's time to zoom out and look at the much larger structure we all live inside. Our galaxy, the Milky Way. If you were far outside it, the Milky Way would look like a vast, faintly glowing disk of light, with spiral arms curling around a brighter central bulge. Embedded in that disk are stars, gas, dust, and dark matter, all held together by gravity. From edge to edge, the Milky Way is roughly 100,000 light-years across. That means a beam of light traveling at 300,000 kilometers per second would still need about 100,000 years just to go from one side of our galaxy to the other. Every star you can see in the night sky with your unaided eyes, every dot of light you've ever wished on or navigated by, is located within a tiny patch of that disk, a small region around the sun, only a few thousand light-years deep at most. Our sun sits about 26,000 light-years from the galactic center, roughly halfway between the center and the outer edge, in one of the spiral arms sometimes called the Orion Arm or Orion Spur. If you've ever seen a picture of a spiral galaxy in a textbook, it probably looks incredibly busy and bright, spiral arms blazing with light. But if you were out there, hovering above the Milky Way like a god, most of it would actually look very dark. Space between stars is almost completely empty, and the stars themselves, though countless, are tiny points separated by huge gulfs of nothing. Within this 100,000 light-year disk, astronomers estimate there are somewhere between 100 billion and 400 billion stars. We're not sure of the exact number. Counting stars from inside the galaxy is like trying to count trees while standing in the middle of a forest at night with a fog machine running. Dust clouds block our view in some directions. Many stars are too faint or too far away to detect easily, but the best estimates suggest that the Milky Way contains at least hundreds of billions of suns. Our own sun is not special among them. It's not the biggest, not the hottest, not the brightest, not the oldest. It's a typical yellow-white dwarf star, about average in both size and luminosity. If you could line our sun up alongside a random sample of stars from the Milky Way, it wouldn't particularly stand out. There are stars hundreds of times more massive than the Sun, burning so hot and bright that they live only a few million years before exploding. There are stars much smaller and dimmer, red dwarfs that quietly burn for trillions of years. There are double stars, triple stars, crowded clusters with thousands of stars packed into small regions, and sparse regions with stars few and far between. All of this is whirling slowly around the galactic center. Our entire solar system, sun, planets, moons, comets, is orbiting the center of the Milky Way at an average speed of about 230 kilometers per second. That's much faster than any spacecraft we've ever built, but on galactic scales, it's just enough to keep us in orbit, like a stone in a sling. At that speed, how long does it take us to make one full circuit around the galaxy? The answer is about 225 to 250 million years. That period is sometimes called a galactic year, the time it takes the Sun to complete one orbit around the Milky Way's core. Think about what that means for life on Earth. The last time the Sun occupied roughly the same position in its galactic orbit that it does today, the first dinosaurs were just beginning to appear. Since then, the dinosaurs evolved into massive, diverse forms and ruled Earth for over 160 million years. A giant asteroid struck, and they went extinct 66 million years ago. Mammals rose, primates evolved, and eventually humans appeared. All of human history played out. Every civilization, every story, every moment we've talked about so far. And in all that time, the Sun has completed less than one full orbit of the Milky Way. We tend to think of days, months, and years because that's what we experience directly. But from a galactic point of view, an entire human lifetime is less than a heartbeat, and the whole history of our species is just a brief flicker during one lap around the galaxy. The light-year scale also shows up when we look in toward the galactic center itself. As we said, we're about 26,000 light-years from the core. So any light we receive from that direction, visible light, infrared radiation, radio waves, has taken about 26,000 years to reach us. That means when we observe the center of our galaxy, we're seeing it as it was 26,000 years ago. 26 millennia ago, humans were still living as hunter-gatherers. Agriculture hadn't yet been invented. There were no cities, no writing, no recorded history. People painted animals on cave walls, followed migrating herds, and told stories around fires. While all of that was happening through every step of human cultural evolution since then, the light from the galactic center that we see tonight was traveling through space, crossing those 26,000 light-years. The same is true in every direction. Look outward along the spiral arm, and you might be seeing young star-forming regions tens of thousands of light-years away. Regions as they were when ice sheets still covered large parts of Earth. Look to other arms or out of the galactic plane altogether, and you're looking at scenes from different points in the Milky Way's past, all layered together onto the sky we see from this one tiny planet. So when we say the Milky Way is 100,000 light-years across, we're saying several things at once. It would take 100,000 years for light to cross it, even though light moves as fast as anything can. Stars on one side can't possibly see the present state of stars on the far side. They only ever see each other's history, tens of thousands of years out of date. Any hypothetical civilization living elsewhere in our galaxy, if it were watching us, would never see Earth as it is now, only as it looked however many light-years separate us. We live not just in a big galaxy, but in a galaxy where time is stretched across space. Our local 20 light-year neighborhood, with its hundreds of stars and growing list of exoplanets, occupies a tiny, tiny region of the structure, a speck in one spiral arm of a disk that itself is just one among billions of galaxies. In the next section, we'll step even farther back and look beyond the Milky Way to the larger universe. Clusters of galaxies, the cosmic web, and distances so great that light has been traveling toward us for billions of years, back to a time when the universe itself was young. We've moved from our solar system to our local stellar neighborhood, and then out across the Milky Way. Now it's time for the biggest jump of all, the scale of the entire observable universe. This is the largest stage on which light years play their role. Astronomers estimate that the universe is about 13.8 billion years old. That's the time that has passed since the Big Bang, the hot, dense beginning from which everything we see today has expanded and evolved. You might think that means the most distant things we can see should be about 13.8 billion light years away. Light leaves them at the beginning, travels for 13.8 billion years, and arrives here today. But the reality is stranger, because while that light has been traveling, space itself has been expanding. The fabric of the universe has been stretching, carrying galaxies along with it. So by the time the light from the most distant objects reaches us, those objects are now much farther away than 13.8 billion light years. When we account for that expansion, we find that the observable universe, the region of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light years. In other words, the farthest galaxies we can, in principle, see today are 46.5 billion light years away now. The diameter of this observable region is about 93 billion light years. That is not the size of the whole universe, only the part for which light has had enough time to get here. Beyond that sphere, there may be much more universe, possibly infinitely more, that we will never see because the light from those regions hasn't had enough time to reach us, and in some cases never will. Inside this 93 billion light-year bubble, the numbers become mind-melting. Observations from telescopes like Hubble and more recent surveys suggest there are on the order of 2 trillion galaxies in the observable universe. 2 trillion. If you tried to count galaxies 1 per second, 1, 2, 3, you'd be counting for more than 60,000 years just to reach 2 trillion. Each of those galaxies contains billions or even trillions of stars. Multiply it out, and you get an estimated total number of stars somewhere between 10 superscript 2 superscript 2 and 10 superscript 2. That's 10 sextillion at the low end, up to 1 septillion at the high end. We don't have good words for numbers this large. We call them 10 sextillion or 1 septillion. But those labels don't help much. They're really just a way of saying more stars than you could ever possibly imagine. And again, that's just within the part of the universe we can see. On these scales, galaxies are not sprinkled randomly through space like grains of sand. When we map their positions in 3 dimensions, something beautiful emerges. A structure known as the cosmic web. Galaxies cluster together in groups and clusters. Those clusters themselves are arranged in vast filaments, long thread-like structures stretching hundreds of millions of light years across. Between the filaments are enormous voids, regions of space that are relatively empty, with very few galaxies at all. If you could step far outside the observable universe and look back, the distribution of matter might look a little bit like a sponge or a network of soap bubbles. Bright filaments and nodes where matter is concentrated. Dark voids in between, where almost nothing resides. Our own Milky Way lives in one of those filaments, bound by gravity to its neighbors in a structure called the local group, which is part of a larger supercluster, and so on up the hierarchy. All of the structure has grown over billions of years as tiny fluctuations in the early universe were amplified by gravity, pulling matter into denser regions and leaving other regions emptier. At the same time, the universe itself has been expanding. This expansion isn't like galaxies flying apart through pre-existing space. It's more like space itself is stretching, and galaxies are being carried along for the ride. A common analogy is a loaf of raisin bread rising in the oven. The dough represents space. The raisins represent galaxies. As the dough expands, the raisins get farther apart. Not because they're moving through the dough, but because there's more dough between them. Another analogy is the surface of a balloon dotted with ink spots. As you blow up the balloon, the surface stretches. Every dot sees every other dot moving away. The farther apart 2 dots are, the faster they recede from each other. That farther means faster relationship is exactly what we observe in the real universe. Hubble's law. Distant galaxies are moving away from us, and the more distant they are, the faster they appear to recede. There's an important detail, though. On small scales, inside galaxies, inside galaxy clusters, this expansion is overwhelmed by gravity and other forces. The space between you and the person next to you isn't stretching. The distance between Earth and the Sun isn't increasing due to cosmic expansion. The Milky Way and its nearest neighbors are gravitationally bound. They're not being pulled apart by the universe's stretching. Expansion only really dominates on very large scales, between clusters and superclusters separated by tens or hundreds of millions of light-years. And here is where light-years take on a new, unsettling role. As we look farther and farther away, we see galaxies so distant that the space between us and them is expanding faster than light could cross it. This doesn't violate relativity, because those galaxies aren't moving through space faster than light. Rather, space itself is expanding between us and them. Locally, nothing breaks the speed limit. But globally, the distance between us grows at a rate that light cannot keep up with. For some regions, that means that light they emit now will never reach us, no matter how long we wait. There is a kind of cosmic horizon, a boundary beyond which events are forever outside our causal reach. Inside the horizon, light has time to get to us, or will eventually. At the horizon, light just barely manages to approach over the lifetime of the universe. Beyond it, expansion carries things away so quickly that their light will never arrive. As time goes on, more and more galaxies cross this horizon from our point of view. Their light gets stretched to longer and longer wavelengths, redshifted until they fade into the background. In the far future, if any civilizations are still around, they will see a much emptier universe. Most galaxies we can see today will have slipped beyond their reach, permanently out of contact. So when we say the observable universe is 93 billion light-years across, we're really saying, this is the bubble of space within which light has had enough time, given the age of the universe and the rate of expansion, to reach us. Beyond that bubble lies more universe, perhaps much more, that is, for all practical purposes, invisible and inaccessible. Our tiny solar system orbits one average star, in one spiral arm of one galaxy, embedded in this enormous cosmic web, stretching tens of billions of light-years in every direction. Light-years, which started as a way to describe the gap between us and the nearest star, now chart the distance from here to the edge of everything we can ever observe. In our final sections, we'll bring this perspective back home, what it means emotionally and philosophically to live in such a vast, old, and ultimately limited universe, and what light-years quietly tell us about our own significance and responsibility within it. We've now zoomed all the way out to the scale of the observable universe. There are trillions of galaxies, and within them, more stars than we can count. Many of those stars likely have planets. Many of those planets may be habitable. Some might even host life. Given all of that, a question naturally appears. If the universe is so big, and the chances for life seem so plentiful, where is everybody? This is the essence of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where's everybody?" over lunch one day in the 1950s. If intelligent life is common, why don't we see clear evidence of it? Light years and the limits they impose are at the heart of one possible answer. Let's start with us. For about the last century or so, humans have been unintentionally broadcasting radio waves into space. Early radio transmissions, television signals, radar pulses, military communications, satellite chatter. All of these spill out into space at the speed of light. If you imagine those signals as forming a growing bubble centered on Earth, that bubble currently has a radius of roughly 100 light-years. That sounds enormous, and on human scales it is. But remember, the Milky Way is about 100,000 light-years across. our radio bubble, everything we've ever sent that could, in principle, be detected by another civilization, is just 100 light-years in radius inside a galaxy 100,000 light-years wide. We've barely whispered into a tiny patch of our own neighborhood. If you shrink the Milky Way down so that it fits inside a circle 1 meter wide on your floor, our radio bubble would be about a millimeter across. A pinprick in the middle of a huge disk. And that's assuming anyone out there has equipment sensitive enough and pointed in exactly the right direction to even notice us. Because those signals fade. As radio waves spread out, they form expanding spheres. The same power is spread over a larger and larger area. The farther you go, the weaker the signal becomes until it's buried in the natural noise of the universe. An old analog TV broadcast from Earth, by the time it has traveled even a few dozen light years, is unimaginably faint. To detect it, an alien civilization would need enormous radio telescopes, tuned to exactly the right frequency, pointed at exactly the right tiny patch of sky, listening at exactly the right time, and they'd have to distinguish that signal from the background hiss of their own star, their own galaxy, and the cosmic microwave background. It's not impossible in principle, but it's hard. We're in the same position. When we search for signals from other civilizations, projects like SETI, we're scanning vast areas of sky at many frequencies, hoping to find something obviously artificial. So far, we haven't seen anything conclusive. One possible explanation is simple and sobering. Maybe there just aren't many technological civilizations at all. But another explanation, equally plausible, is that there are other civilizations, maybe many of them, but they're separated from us by light years so vast that communication is basically impossible. Imagine intelligent species sprinkled through the galaxy like lights on a huge, dark grid, but separated by thousands or tens of thousands of light years. Even if they all broadcast radio signals for a while, each would only illuminate a tiny bubble around its own star, maybe a few hundred light years at most, before their civilization faded away or moved on to other forms of communication that are harder to detect. Their bubbles might simply never overlap with ours. We could be shouting into our own small sphere of space, while someone else, thousands of light years away, shouted into theirs millions of years ago. Their light has long since passed by us before we were here to listen. Or it may never reach us at all because the space between us is stretching too fast. From our vantage point, the universe would look silent. From theirs, it might have looked silent too. This leads to a haunting possibility. The universe could be full of civilizations, each one living, thinking, building, wondering, but most of them so far apart in space and time that none of them ever have a meaningful conversation. Each one trapped inside its own light-year bubble, forever separated by the very laws of physics that make the universe possible. There's a deep emotional tension in this idea. On one hand, it paints a picture of a lonely universe. We may be effectively alone in our part of the galaxy, not because no one else exists, but because even if they do, they are too far away for us to ever truly know them. On the other hand, it allows for a crowded universe, one buzzing with life we will never meet. A universe where curious minds under other suns look up at their night skies, ask the same questions we ask, and hear the same silence we hear. In both cases, the result from our perspective is the same. We don't hear anyone. We don't see undeniable signs of cosmic engineering. We don't receive clear messages spelling out, "You are not alone." Light years turn potential neighbors into distant ghosts, their signals smeared out, delayed, or lost entirely. It's possible that each civilization, no matter how advanced, lives and dies in isolation, bounded not just by the limits of its own imagination and resources, but by a shell of light years beyond which it can never really reach. If that's true, then what we do here on this small world matters in a special way. We might be the only intelligent life for dozens, hundreds, or even thousands of light years in any direction. Our thoughts, our art, our science, our kindness and cruelty, our entire story might be utterly unique in this patch of space. Light years don't just separate us from hypothetical aliens. They also focus responsibility back onto us. In the final part of this journey, we'll bring all of this together: what light years mean for our sense of scale, for our daily lives, and for how we choose to live on this tiny planet orbiting an ordinary star in a universe that is vast, ancient, and perhaps, in a very real sense, silent. We've covered a lot of distance tonight. We started with something that sounded simple, a light year, and followed it all the way from the space between your house and the grocery store, out past the moon and the sun, beyond our neighboring stars, across the Milky Way, and finally to the edge of the observable universe. Before we drift off, let's gently gather the pieces together. A light year, we learned, is not a measure of time at all. It's a distance. The distance light travels in 1 year, moving at about 300,000 kilometers per second. When you multiply that speed by every second in a year, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year, you get a number, roughly 9.46 trillion kilometers. That's 1 light year. We saw how that unit solves a problem. Kilometers and miles simply fall apart in space. They turn into walls of zeros that our brains can't understand. Light years give us a cleaner way to talk about distances that involve trillions of kilometers and millions of years. Our closest stellar neighbor, Proxima Centauri, is 4.24 light years away, about 40 trillion kilometers. Even with the fastest spacecraft we've ever built, it would take thousands of years to get there. Even with bold ideas like laser-push sails racing at a fraction of light speed, it would still be a journey measured in decades, with no way to slow down and years of delay before any signal could return. We zoomed out and saw that our home galaxy, the Milky Way, is about 100,000 light-years across. The light from its center takes 26,000 years to reach us, so we see it as it was when humans were still hunter-gatherers. The galaxy holds hundreds of billions of stars, most of which we'll never know we exist. And then we stepped back even further to the observable universe, a bubble roughly 93 billion light-years across, filled with trillions of galaxies and an unthinkable number of stars. Light-years became more than just markers on a map. They became a way of seeing that distance and time are inseparable. Every light year between us and something out there also marks how far back in time we're seeing it. The speed of light is a hard limit. No signal, no ship, no technology we know of can outrun it. Together, those facts mean the universe isn't just big. It's also deeply, permanently separated. There are places whose light will never reach us, and places we will never reach, no matter how clever we become. It's easy, looking at these scales, to feel very small. Compared to billions of years and billions of light years, a human life is a flicker. 80 or 90 years, if we're lucky, against a backdrop of 13.8 billion. One small planet orbiting one ordinary star in one galaxy among trillions. From that perspective, our conflicts, our deadlines, our worries about next week or next year can seem almost weightless. The argument you had today, the email that stressed you out, the mistake you keep replaying in your head, all of it is real. All of it matters to you, and that matters. But in the grand scheme of things, these moments are local, temporary, and small. They're ripples on the surface of a vast ocean. Sometimes, remembering that can be strangely comforting. The universe is not watching your every move. The stars are not judging you. You are allowed to be imperfect on this little world, to make mistakes, to try again. The cosmos rolls on, patient and indifferent, while you figure things out at your own pace. But there's another side to the story. For all our smallness, there is something extraordinary about us. From this one tiny planet, using tools we built with our own hands, we have measured the speed of light, mapped the distances to nearby stars, traced the structure of our galaxy, estimated the size and age of the observable universe. We've discovered that time runs differently for fast-moving particles and satellites in orbit, and we've used that knowledge to make GPS work. We've watched muons live longer than they should, and understood that as proof of time dilation. We've seen galaxies billions of light years away and realized we are literally looking back in time at a universe that was young. In a sense, the universe has spent billions of years evolving from simple hydrogen gas into stars, into heavier elements, into planets, into chemistry, into biology, and finally into minds that can look back and say, "Oh, that's what I am a part of." The atoms in your body were forged long ago in the hearts of stars. Stars that lived, burned, and died before our sun was even born. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was cooked in ancient stellar furnaces and scattered across space in supernova explosions. Those atoms drifted through the galaxy, joined together in a cloud, collapsed into a new star and a new set of planets, and eventually became you. When you think about light years, when you contemplate galaxies and cosmic webs and the speed of light, it is the universe thinking about itself. You are, quite literally, a small part of the cosmos that has become aware enough to measure its own size. That realization doesn't shrink you. It doesn't mean your life is meaningless. If anything, it makes you more precious. Because in all the vastness we've talked about tonight, in all those hundreds of billions of light years, and all those countless stars, consciousness, as far as we know, is rare. It may exist elsewhere, probably does, but it is certainly not everywhere. Here, on this one world, at this one moment, there is you, a brief, unique arrangement of stardust capable of love, curiosity, fear, joy, regret, and wonder. Your problems are small compared to galaxies, yes, but they are not small compared to you. They fill your inner universe, and that universe matters because you are the only one who will ever live it from the inside. If the cosmos is largely silent and unreachable, then what we do here with each other takes on a special weight. Kindness matters, honesty matters, curiosity matters, because for light years in every direction, there may be no one else asking these questions, no one else telling these stories, no one else turning the raw facts of physics into meaning. So the next time you step outside on a clear night and look up at the stars, remember what you've learned tonight. Those points of light are not just decorations on a black ceiling. They are suns, many with their own planets, scattered across space by light years. The light reaching your eyes has been traveling for years, decades, centuries, or longer, carrying messages from the past. Sirius shows you what it looked like 8.6 years ago. Vega sends you light from 25 years ago. Betelgeuse whispers stories from the Renaissance. The center of our galaxy sends you photons that left when humans were still painting on cave walls. You live at the bottom of a deep, four-dimensional sky, where every direction is also a direction in time. Thank you for staying with me on this long journey through space and time. If you'd like to take more of these slow, deep trips into the universe, a like or a subscribe helps more than you might think. But for now, you don't need to do anything at all. Just let your eyes close whenever they're ready. Out there, light continues its endless travel across billions of light years. In here, on this small planet, you get to rest. Sleep well, and may you never look at the stars quite the same way again.